Okay, so far in this chapter, we've been thinking about very smooth, kind of neat, orderly flowing of liquids or gases as they move from place to place, right? We had, for instance, a horizontal pipe, and all of this water was just smoothly flowing in this direction. In the center of the pipe, it was moving a little bit faster than in the edge of the pipe, but it was all just kind of nice, neat, smooth flows. And even when we had water going around a bend, you could kind of trace the nice smooth path that any particular kind of stream of water would take. So a stream of water near the outside of this pipe, would be moving at some velocity. It would slow down as it got to this high pressure region. It would speed up a little bit as it got back to kind of the typical pressure within the pipe. But all of these liquids would be flowing in kind of nice, smooth little lanes, right? And in fact, if I were to put little, say, drops of food coloring in, say, this pipe, if I put a drop of food coloring right here, I would just see that food coloring kind of follow this neat, smooth little line of water. And if I picked a different color and I put a drop of food coloring in the middle of this pipe, that food coloring would be swept along this kind of streamline, this kind of line of flow for this water. Right? So I would see in this kind of experiment of dropping little bits of water in, two kind of streaks of color following these lines, these streamlines. And those lines of color would neither mix very much, nor would they get like a lot farther away from each other. And this kind of smooth, kind of neat, orderly flow is called laminar flow. Right, so this is all called laminar flow. Laminar because it refers to fluid moving in kind of nice, smooth layers. So laminar flow tends to result when viscosity is dominating the flow of this liquid, right? Because viscosity is trying to stop nearby parts of a fluid from moving very differently from one another, right? Viscosity acts to oppose the relative motion of one layer of water from another. And so if you have very viscous flows, they tend to follow these neat, smooth, orderly streamlines, right? We all know, though, that flows can be a lot more chaotic than this, right? If you watch a river, you can see rapids where, though, you don't have a neat stream of water, you have like a roiling, crashing, stream of water sweeping over rocks, plunging into other parts of water, churning the water, mixing everything up. It's really, quite a lot noisier and messier and more fun than these kind of smooth laminar flows. And that kind of messiness is called turbulence, or if you're comparing flows, laminar flow versus turbulent flow. And so if I look at, say, the flow of something within a pipe, if it's turbulent, rather than having these nice, neat, orderly streamlines, I'll have wild, crossing, mixing, crashing flow that swirls back on itself, surges forward, back and forth, right? And if I put two little drops of food coloring, for instance, or dye in the water at two different parts, they will very quickly just kind of mix and become a gross little blob of multicolor just a short distance later. So if laminar flow is dominated by viscosity, turbulent flow is dominated by inertia. The idea is that if you look at any little parcel of water, look at a little packet of water, it's moving with so much internal momentum that the viscous forces are not enough to really change its direction substantially or make it slow down to match the velocities of nearby parts of water. So all of these little parcels of water are all just going in their own directions, moving with too much momentum for these viscous forces to line everything up, right? And it's important that flows can transition back and forth between laminar and turbulent regimes. So for instance, if you look at a stretch of river, you can have a portion of the river where everything is flowing nice and calmly and smoothly, followed by a section of rapids, really violent, turbulent whitewater, and then the river can go back to smooth laminar flow. So you can transition back and forth between these different types of flow patterns, right? And so in the rest of this chapter, where we're going to be thinking about, like, especially the aerodynamics of, for instance, tennis balls or baseballs or footballs or whatever flying through the air, we're often going to need to think about, well, is the air flowing around an object laminar, smoothly flowing? Is it turbulent? Is it a mix of these two kinds of flows? And this is going to depend on a lot of the details of what's going on, right? It's going to depend on what fluid the object is moving through. So if you, wave a canoe paddle through the air versus through water, you'll get potentially different types of flows. It depends on how fast you move an object through a fluid, or how fast you flow an object over, how fast you flow the fluid over that object. It depends on the density of the fluid. It depends on the size of the object, all of these things. So how can we combine all of these different things that this distinction between laminar and turbulent flow depends on into a kind of a way of determining whether flow will be turbulent or laminar? So how can we tell if flow will be turbulent or laminar? Actually, we already found the answer to this question, or we briefly discussed it at the very beginning of this class, back in chapter 1, when we introduced the idea of the Reynolds number. Right? So the answer is this Reynolds number, and Reynolds was his last name, so there's no apostrophe here. The Reynolds number, the symbol that we use for the Reynolds number is this RE, and in words, the Reynolds number is determined by the following things. You've got the density of the fluid multiplied by like some characteristic size of the object. So I'm going to write this as object's size multiplied by the flow speed, all divided by the viscosity of the fluid. Okay. And in symbols, as perhaps you saw on the midterm, or again back in chapter 1, you might write this as the density of the fluid times a characteristic size times a flow velocity, a flow speed, divided by the fluid viscosity. Okay. So this Reynolds number is really useful for determining as an object moves through a fluid, or as a fluid moves over an object, is the flow going to be laminar or turbulent, right? So most of these, I think, are pretty self-explanatory. So density of the fluid, what is the density of air? What is the density of water? The mass density, okay? The flow speed, how fast are you moving the object through still air? Or how fast is, say, the wind blowing over some object? And then the fluid viscosity, that's the kind of thing that we introduced back in section 7.1. And then this L, this kind of characteristic size of the fluid, or of the object, this refers to a characteristic linear size of some object. So it might be the radius of a sphere, if the object's a sphere. If it's a cube, it might be like the length of the side edge of that cube, so on and so forth. And I'll compute a few specific examples of this in a second, but one of the things that I want to tell you is that this researcher, Reynolds found empirically that if the Reynolds number was less than something, about 2300. By the way, you'll notice this combination, density, length, velocity divided by viscosity, actually has no dimensions. So there's no units associated with the Reynolds number. It's a pure number. So Reynolds found that if that pure number is less than about 2300, you got laminar flow. You got laminar flow. And above that, if Reynolds number, bigger than this, you're getting into turbulent flow. Okay, so this Reynolds number then kind of gives us a quantitative point of comparison, a quantitative thing that we can compute if we see an object moving through a fluid or a fluid moving over an object, to let us know, well, should we expect the fluid flow to be smooth and laminar or kind of chaotic and turbulent, right? I'll compute this number several times over the rest of the chapter. Just to kind of illustrate this kind of transition between laminar flow and turbulent flow is the kind of thing you can observe just by moving a spoon through water at different speeds, right? So for instance, let's think about spoon moving through water. Okay, so if I think about the kind of fat part of a spoon, I've got some blob like this. This looks more like an upside down lollipop, but you get the idea. And the kind of diameter of this spoon, if I just think about what I have in my kitchen, it has a width of maybe 2.5 centimeters or something, 2.5 centimeters. Okay, so suppose I move the spoon through water through water at, say, 5 centimeters per second. Right, and that's like 2 inches per second, which is really not very fast, right? So if I have a space that's 2 inches and I count 1 second, that's pretty slow motion, okay? So if I move the spoon through water at 5 centimeters per second, well, what's the Reynolds number? The Reynolds number will be about, the density of water. We can say it's maybe about 977 kilograms per meter cubed. The characteristic length here, 2.5 centimeters. I can write that as 0.025 meters. If I'm moving it at 5 centimeters per second, I can say that's 0.05 meters per second, just so that all of my units are agreeing here. And then what's the viscosity of water? Back up in, I think section 7.1, we quoted some numbers just to give us a sense of scale. Water at room temperature, maybe it's about 10 to the minus 3 Pascal seconds. And so the Reynolds number of moving a spoon slowly through water is about 1250 with these numbers that I've picked, right? And that should kind of accord with your experience of interacting with the world, that if you move a spoon really slowly through water, the flow of water around that spoon is really like nice and smooth. It's laminar, okay? Now, what if I move the spoon quicker? Move the spoon at, say, 50 centimeters per second. Well, half a meter in 1 second. That's quite a bit faster. If you do that experiment, what you'll see is that, when you just start from rest and then just move it at that velocity through the water, you'll really mix up the water, and there'll be like probably a little vortex of water that flies off behind the spoon, and you will see turbulent flow, right? And if I compute the Reynolds number, I can plug in these same numbers, except now instead of 0.05 meters per second, I have 0.5 meters per second, and I'll get a Reynolds number, which is about 12,500, right? And so that lets me know that I should have expected, even without doing the experiment, that I'll probably see turbulent flow, whereas here I saw laminar flow. Okay. Great. And one of the things that I also want to emphasize is that it really doesn't matter if I'm thinking of moving like the spoon through water or flowing water past a spoon that I'm holding still. And so in fact, in the rest of this chapter, while we think about like how curveballs work and how flow around sports balls work in general, we'll be free to go back and forth between kind of having our frame of reference moving with the ball so that the ball looks like it's staying stationary and air is flowing over it, versus a different frame of reference where we're observing things and the ball is moving quickly through still air. Okay. So in the next section on aerodynamics, we'll start thinking about all of these fun effects of objects moving quickly through fluids.